So now we need to discuss the tail, what we call the tail behavior. And these are the non-vertical asymptotic behavior, the non-vertical asymptotic behavior. So we're finding non-vertical asymptotes, which will include horizontal asymptotes, slanted asymptotes, which are and then functions approaching other functions asymptotically. So those are the three things we'll talk about here. I think there's a couple of videos on this. So the tail behavior of a graph is its behavior as x goes to negative infinity and as x goes to infinity. And the left tail, which is going to negative infinity, can behave differently than the right tail, which is x goes to infinity, in general for a function. Okay? For rational functions, they basically, well, yeah, it's still different. But if they have an asymptote, it'll be the same asymptote for both with rational functions. So there's four possibilities for a rational function. One, the degree of q. Remember, p is the polynomial in the numerator, and q is the polynomial in the denominator of the rational function. So this says if the degree of the denominator is greater than the degree of the numerator, then the asymptote is y equals 0. So that's the easy one. So for example, f of x equals 2x minus 1 over 3x squared minus x plus 1. That has an asymptote at y equals 0, the x-axis, y equals 0. That's because as you put in larger magnitude values of x, that x squared becomes big much faster than the x in the numerator does. So the denominator gets big much faster than the numerator does. So this is how it works. As x goes to negative infinity, those terms, the 2x minus 1, the minus 1 just becomes some small round off. Imagine you're at negative 2 million. Then you have 2x minus 1 is 4 million minus 1. And the 1 is really just minuscule compared with the size of the rest of the number. So we say the dominant term there is the 2x as x goes to negative infinity, okay? And the similar thing happens with the denominator. If you have, say, 1,000 even, 1,000 for x, in the denominator you see, well, that'll be 3 million minus 1,000 plus 1. So 3 million plus 999. The 999 isn't very big. If you were going to round it off, you would probably just round it off to 3 million, right? So the minus x plus 1 doesn't contribute very much relative to how much the 3x squared contributes to the size of the number when x approaches negative infinity. And the disparity between those becomes even greater the further out towards, the left side of the number line. The further you go towards negative infinity, the greater, the less the minus x plus 1 matters. Okay, so I say here, as x goes to negative infinity, f of x goes to 2x over 3x squared. And that, of course, reduces to 2 over 3x. And then hopefully you can imagine, as the magnitude of x becomes large, say negative 1 million, that would be like 2 over negative 3 million. Hopefully that's very, very close to 0. So as x gets closer to negative infinity, or as x moves to the left on the number line, that number 2 over 3x becomes closer and closer to 0, which is why the horizontal asymptote is y equals 0. Okay? So you have to kind of imagine these things and think about them a little bit. So I just wrote that out for you. So f of x approaches the horizontal asymptote y equals 0 as x goes to negative infinity. Now you might notice as x goes to infinity, what matters with these rational expressions is that the magnitude is getting large. That is, the distance from 0 is getting bigger and bigger. So the same exact thing is going to happen as x goes to infinity as well. That's why they have the same asymptotic behavior on left and right. Okay, so as f of x goes to 0 as x goes to infinity, so f of x approaches the horizontal asymptote y equals 0 as x goes to infinity as well. So the left tail and the right tail both approach the x-axis, y equals 0. So rational functions are kind of nice this way. There's other functions that don't do this. So it's a special property of rational functions. So that's what I'm noting here. Rational functions have at most one horizontal asymptote, but other functions can have two. And this is not a rational function. This is some other function that I just graphed. I just made up a graph for it. It's obviously a function. It passes the vertical line test. And it has two different asymptotes, horizontal asymptotes. And you can't have three because that will force it not to be a function. You might have to think about that a little bit to see, because there's only two tails, a left tail and a right tail. If you had third, you'd need a third tail. And that doesn't make any sense in 2 dimensions. Okay, so